Now we're going to see if we can apply what we just learned about elasticity and how to measure it by cooking a steak. So we have a steak here, and we're going to see if we can quantify the mouthfeel of the steak as it cooks by measuring the elasticity. And in order to do this scientifically, we've cut out little pieces of steak, and they all have the same dimensions. They're 4 centimeters by 4 centimeters. And we're going to measure the height of these steak pieces, and then we're going to apply a weight to the steak and see how much they compress. And we're going to do this first with a raw piece of steak, and then we're going to cook the steak to medium and see how the elasticity changes. So this will be an exercise in how to calculate the elasticity of a food. So we're going to do it with steak, but you can really do this with any kind of food that is elastic. So here on the right, I'm showing you a little setup for how to measure elasticity. So we have a ruler and we have a plastic plate and we have weights that we use to compress the steak with, and the weights are 200 grams total. So if we now want to find out what the elasticity is, we will use our equation, and we know that the elasticity equals the stress over the strain, and the stress is the force over the area, and the strain is the delta height over the total height. So we already know a few things here. I already told you that the area of the steak piece is 4 centimeters by 4 centimeters. I'm going to correct that here. And this ends up being 16 centimeters squared. I also told you that the mass of the weights was 200 grams, and so the force is the mass times the gravitational constant. So we then have 0.2 kilograms times 10 meters per second squared. And then we can measure our heights. So initially, without a weight, we can see that the height is about 30 millimeters. And then after this, it's a little bit hard to see here, but after we add the weights, the height is about 26 millimeters. So the delta L then is going to be 4 millimeters. And this is our L here. So we're using our original height of the steak for L. So now we can just plug into our equation. So the elasticity then equals 2 newtons over 16 centimeters squared over 4 millimeters over 30 millimeters. And 16 centimeters squared is the same as 0.0016 meters squared. And the millimeters cancel out. And so we end up with 9,400 newtons per meter squared. So this is our elasticity for the raw steak. So now I'm going to go and do the same thing for the cooked steak, and we'll compare our numbers. So we cooked our steak to about medium, and here's the setup again, showing the steak without any weight on it, and then with the weight on it. It's the same weight, it's 200 grams. And the equation, of course, is the same, and a lot of the values in the equation are the same because not much has changed. So the force is the same because I told you that the weight was the same, and the area is also the same. It's 4 centimeters times 4 centimeters. I'm correcting it again, 16 centimeters squared. And it looks like the original height is 30 millimeters, so it's the same. And the final height after we've added the weight is 28 millimeters. It's a little bit difficult to see. So it's not a huge change. It's 2 millimeters change, which is about half. So it's not huge, but it's still half of what we saw with a rare steak. So if we now plug this into our equation, our force, our area, our delta L, and our L, we end up with 18,700 Newton per meter squared. So this is about double the elastic modulus that we got for steak, which was 9,400 Newton per meter squared, which we could probably expect because the change in the delta L is about half. So next let's see if we can understand this doubling in elastic modulus by understanding what's going on the molecular level. So I'm going to show you this in the next slide. Okay, so let's focus first on this top part of the slide. this is basically our mental picture of what a steak looks like on the molecular level. So this is the cross links indicated here, and we're showing you that each of them has a bond length L, and we're not writing it out here, but Dave also told you that each of them have a energy U interaction, which we learned about earlier in the semester. And so what we have talked about before is that elasticity is basically a measurement of energy density. And so as the elasticity goes up, as the elastic modulus goes up, there is an increase in energy density. And since Dave told you that in foods, bonds, the energy of bonds, so U interaction, is usually about the same. It doesn't change much. And so when we experience an increase in elastic modulus, what it usually means is that there is an increase in bond density. So there are more bonds, and because of that, the bond length is shorter. So with this in mind, let's calculate the bond length of each of the elastic moduli we got for the raw steak and for the cooked steak. And here's two pictures, so you can even see that they're very different looking. So for this, we can use the equation, the other equation that we looked at this week, which says that the elasticity equals the interaction energy over the bond length cubed. So if we solve for the bond length, we end up with this expression. And if we then plug in what we already know from earlier in the semester is that U equals kBt, and we divide by the elastic modulus, and we plug in the Boltzmann constant here, and the temperature, which is at room temperature because the raw steak is at room temperature, and then we have our elastic modulus 9,400 newtons per meter squared. And so it turns out that this is 7.6 times 10 to the negative 9 meters. And so if we do the same thing for our medium steak using the same equation, the Boltzmann constant, and here we're using a temperature of 330 kelvins because the temperature of the medium steak is actually higher than room temperature. It's about 60 degrees Celsius. And we're using the elastic modulus we got from before, and this ends up being 6.2 times 10 to the negative 9 meters. So the first observation to make is that both of these numbers are small numbers. They're on the order of nanometers, which makes sense. These are bonds that are happening on the molecular level where nanometers or angstroms, which is 10 to the negative 10, is usually the order of magnitude. The second thing to note is that the bond length actually did become shorter. So it went from 7.6 nanometers to 6.2 nanometers. So this is a decrease by about 20%. So even though we measured only a small difference in the compression of the steak, it was only a matter of millimeters, we still see a change in the bond length that is about 20%. Now, of course, these numbers are approximate, and they're sort of just giving us an idea of what would happen on the molecular level, but they're by no means precise. The take-home message is that the elastic modulus and what you can measure on a macroscopic level is closely, intimately connected to what is going on a microscopic level, and this is giving us some indication of that.